Okay, hello everyone. So let's continue our lecture on the fundamentals of environmental engineering. And so this class we're going to continue reviewing some basic chemical concepts so that we can apply these concepts into water treatment and wastewater treatment. So before we do that, let's do a quick recap of what we have learned in our last class. So in our last class, we mainly went through quite many basic chemical concepts, right? For example, including what is atomic number, what is the mass number. So this is related to the structure of the elements. And also we learned what are ionic, covalent, and hydrogen bonds. And these are related with the forces being applied onto the ions or the elements. And also what are the mole, molar weight, molarity, and normality. So in this class, we're going to learn more about the molarity and normality in the water and wastewater treatment, and also how to calculate them. Furthermore, we learn how many types of chemical reactions do we normally see. For example, we have the redox, basically the reduction oxidation reactions, right? We also have the precipitation reactions. And also, what is a solubility product? What is the acidity constant? So how do we calculate the final concentrations of a reactant for zero, first, and second order reactions, right? And also, what is the temperature influence onto the reaction rate? So we have some empirical equations that can consider the temperature influence onto certain reaction rates, right? So in this class, we're going to learn more of the basic concepts that can be used in environmental engineering. So we're going to learn basic concentration units, and especially the normality. So this is a quite new concepts that we're going to use. And also we want to know the carbon dioxide system. What is the pH of rainwater? Because there are a series of dissociation reactions that will determine how the hydrogen ions are being released in water. And also we want to define the alkalinity, and alkalinity is actually a very important parameter for the water and wastewater treatment. So first, we want to learn some basic concepts that can be used in water chemistry. And here I'm going to quickly go through some definitions that we used before. For example, the density, we know that quite well. Actually, the density is a mass per unit volume in kilogram per meter cube. So it does not change with the location, right? It doesn't matter whether we measure it at the surface of the Earth or in the space station. So there's another definition called the specific weight, and the specific weight is related with the gravity. It's basically the force per unit volume, and that can be represented in kilonewtons per meter cube. So basically, this specific weight, or gamma, can be calculated by rho multiplied by g, where g is the gravity. And the gravity can be different at different locations, right? The higher the, basically the higher in the sky, then the lower the gravity, or the acceleration of the gravity, right? So there's another concept called the specific gravity. We normally use S as the parameter or as the symbol. So that is the density or specific weight relative to water. So for example, the mercury have a density of 13.6 grams per centimeter cube. So that's 13.6 times compared to the 13.6 times of the water density. So under this situation, the specific gravity for mercury is going to be 13.6, which also means that it's 13.6 times heavier than water. And based on these definitions, we can know that specific gravity can be also represented by the ratio of the density of certain object or certain species over the density of water, or the specific weight of certain species over the specific weight of water. So in water chemistry, we're also going to use the viscosity of the water. So the viscosity is defined as the internal fraction resistance to the movement. So basically, the higher the viscosity, then the more difficult it is to move certain liquid. to cause a movement to this liquid. So basically, the greater the viscosity, the greater the sheath force that it will going to require to make it move. And in terms of the parameters that we can use to quantify the viscosity, we can either use dynamic viscosity, or that's also called the absolute viscosity. We normally use mu, and mu is going to have a unit of kilogram per meter per second or Pascal per second. So basically, these two units are the same. And we can also define a kinematic viscosity, and the kinematic viscosity includes the influence of the density for the liquid or gas species. So that can be calculated by nu equal to mu divided by rho. And based on that, if we plug in the density of the plug in the unit of the density, we're going to have the unit of meter squared per second. So in water chemistry, we're also going to deal with basically the mixture of species that can be interacting with the water. So for these extra species, they can exist in different states. For example, they can exist in the dissolved materials, which means that they can be removed using distillation, precipitation, adsorption, or extraction. So distillation means the purification of the water through evaporation. So basically, we know that if we're having a field trip outside and we need clean water, what we can do is that we can collect the rainwater and evaporate them. So further collect them with some devices at top of it, right? So this process is called the distillation. So that will basically evaporate all the water contents into the gas species, into the gas phase, and they can further get condensed and then collected, while the remaining or the dissolved materials will remain in the solid phase because they cannot be easily evaporated. We can also use the precipitation method. So what that means is that we can add another chemical into the solution and then to form liquids. So basically these to form solids. So basically these solids will precipitate or settle down within the liquid mixture. And this method is commonly used in the softening process, and we're going to learn that in the water treatment. We can also use the adsorption. So adsorption means that we can add in extra solids. For example, people can add in sand into water because sand can have a relatively larger surface area, and this surface area can absorb other species from the water. So basically, we can also use the activated carbon, and that can remove the heavy metals or organic matter. And we can also use the liquid extraction. So basically, that means what that means is that we can extract the substance using another liquid, which means that these extra species in water probably can better get dissolved into this another substance, right? So in this case, we can separate the extra species from the water. So these extra species can also exist in the form of suspended solids. So they can be removed by sedimentation, filtration, flotation, and centrifugation. So what that means is that if we have larger particles or larger suspended species in the water, then we can just let it still there so that its gravity is going to remove these extra solids. And we can also use the filtration, for example, use the sand to collect all of these extra solids, right? And we can also use the centrifugation, because if we create a rotational movement, then basically these larger solids will need a larger centrifugal force to sustain their rotation. If they don't have that extra centrifugal force, they can be basically get removed from the water or from the liquid phase. And there can also be colloid materials. So what that means is that they are also categorized as solids, but they are in the range of 1 nanometer to 1 micrometer. And they cannot be easily removed by sedimentation because the mass of them or the gravity on these small particles are so small. So it's going to take a very, very long time for them to get removed by sedimentation, right? So Under this situation, we can use the coagulation, flocculation, sedimentation. So this is a conventional method. And we can also use the ultracentrifugation. So what that means is we can create a very strong rotation movement of the liquid so that we can remove these smaller particles. Or we can just use a membrane filtration to get rid of these particles. So in water chemistry, there are also other concepts that we need to know. So for example, we need to know what is the molarity. So the molarity is typically represented by this capitalized letter M. So that means the number of moles in a liter. For example, if we prepare a solution that's containing sodium chloride, right? We know that its concentration is 1 mole per liter. Then the molarity is going to be 1m. Okay, so this is a convention. For example, if we decide to choose, prepare another solution of sodium chloride, which is containing 1.2 mole per liter, and then that's going to be 1.2 m. So this is the molarity. So after we know the molarity, we can easily convert from these concentrations, from this molarity into mass concentration, right? So basically, we can convert, if we know the molarity, and then we can measure or we can multiply the molecular weight of these species to get its mass concentration. And normally, for mass concentration, we use the unit of milligram per liter. So in this case, we know that for sodium chloride, let's say that the molarity is 1m, then we know that sodium chloride has a molecular weight of 23 plus 35.5, which is equal to 58.5 gram per mole. So how do we calculate the mass concentration of sodium chloride in the liquid? So that can be quite easily calculated by, so basically the mass concentration, let's say this is defined as X. We want to represent it in the unit of milligram per liter. So that's going to be 1m. So we know that 1m is equal to 1 mole per liter, right? And then we're going to multiply the molecular weight of sodium chloride, that is 58.5 gram per mole. So we can see that in terms of the unit, mole can cancel out, which is going to be equal to 58.5 gram per liter. So please notice that here the units are a little bit different, right? So we want to convert it into milligram per liter. So we're going to multiply by 1,000, right? So that's going to give us 5.85 multiplied by 10 to the 4th milligram per liter. So this is how we can, based on this equation, to calculate or to convert the molarity into mass concentration. And in terms of the mass concentration shown in milligram per liter, we can also notice that, or we can also call that as ppm for water. So for example, if we prepare a solution that's containing 1m of the sodium chloride, then we can know that we can also say that in this sodium water solution, we're containing 5.85 multiplied by 10 to the 4th ppm of sodium chloride. So why is it? That is because if we try to represent the mass fraction, so basically we're converting this mass concentration into the mass fraction shown in ppm. So we first need to convert the liter here into the mass of water, right? So for dilute solutions, 1 liter represents 1,000 grams, right? We also know that 1 milligram represents 10 to the minus 3 grams. So basically, 1 milligram per liter is equal to 10 to the negative 6 grams of the solute over grams of the water. So what this means is that 1 milligram per liter is can be approximated by 1 ppm, of the solute. So this is how we can convert the mass concentration into the mass fraction of the solute, right? And for example, for the other units, for example, we're having a further lower value or smaller value of the mass concentration, then 1 microgram per liter is equal to 1 ppb, because ppb is parts per billion, right? So that's 10 to negative 3 of the ppm. And 1 nanogram per liter is going to 1 ppt, which means 1 parts per trillion. So to represent the concentration of the solute in water or other species in water, we can also use the percent, and that can be either by weight or by volume. So if it's by weight, then we're talking about the fraction again. So you know that for 1 ppm, in terms of weight, then that means 10 to the negative 6 in terms of the mass fraction, right? And if we further try to represent that into percent, then that's going to be 10 to the negative 4%, right? Because 1% is 10 to the negative 2 in terms of the fraction. So now we can get into the definition of normality. And I have to mention that the normality is a quite complex definition, but if you follow me by step by step, you'll see that how we can use that in environmental engineering, right? So by definition, the normality means the number of equivalents per liter. So this equivalent can be anything, right? It can be it can be using any references. For example, it can be hydrogen, right? In water treatment, we want to use calcium carbonate, right? It also can be sodium chloride, or it can be anything. So it means the number of equivalents per liter, and that can be in reference of any chemicals. And this is also calculated, or the normality is also calculated by the mass concentration of this species. For example, we're talking about the sodium chloride again, and then divided by the equivalent weight, okay? And then the equivalent weight, as you can see, that should be in terms of other species. So equivalent weight is calculated by the weight per electron or proton transfer, okay? For example, if we're talking about NaCl again, then this number, this electron or proton transfer is going to be equal to 1. And then if we're talking about sodium carbonate, we know that there are 2 electrons basically carried by the carbonate ion. Then the Z is going to be equal to 2. And we can also apply this into the oxidation reduction reactions, and that also concerns the electron or proton transfer from these oxidation or from these chemicals. Okay, so the equivalent weight is calculated by dividing the molecular weight of a compound. So that can be of any compound, right? Let's say we mentioned about the calcium carbonate, right? We can mention about the hydrogen there, and right? So that is calculated by dividing the molecular weight of that compound by the number of electrons or proton transfer. So here I can give you some more examples. For example, for the acid-base reaction, the Z is the number of protons it can uptake or release. For example, if we're talking about the sulfuric acid, right? So we know that the sulfate ion carries 2 charges, right? So under this situation, the Z, which is number of protons or electrons it can provide or release, right? The Z is going to be equal to 2. And then we know that the molecular weight of the sulfuric acid, let's do a quick calculation, that's going to be 1 multiplied by 2 plus 32 plus 16 multiplied by 4, right? So that's equal to 34 plus 64, which is giving you 98 gram per mole, right? So under this situation, the equivalent weight for the sulfuric acid is going to be 98 divided by 2, which is 49, right? So this is, if we want to represent its unit, that's also shown as gram per equivalent, and we're showing this abbreviation here. And for the sodium carbonate, similar to the sulfuric acid, Z is equal to 2 because this is mainly contributing from the carbonate ion. So under this situation, the molecular weight for the sodium carbonate, so let's do another calculation, right? So 23 multiplied by 2 plus 12 plus 16 multiplied by 3. So you have 46 plus 12 plus 48. So this is going to give us 106 gram per mole. And so since the Z is equal to 2, then the equivalent weight for the sodium carbonate is going to be 53, which is 106 divided by 2. And for the sodium bicarbonate, we see that sodium carry 1 charge, right? And bicarbonate ion carry 1 negative charge. So Z is equal to 1. And the molecular weight is 84 gram per mole. So the equivalent weight for the sodium bicarbonate is 84. And for sodium chloride, for the hydrogen chloride, right? So we have the Z equal to 1, and then equivalent weight equal to 36.5. And the calcium carbonate is going to give us a equivalent of 50 per equivalent, right? So with the definition of the equivalent weight, then we can calculate what normality really means. Similarly, for the oxidation reduction reactions, Z is the ability to uptake or release electrons. So typically, we're going to use the potassium dichromate for the COD test. So COD here represents the chemical oxygen demand. This is a parameter that basically relates to the quality of the water. So we're going to use this chemical to oxidize certain organic matter in the water. So after the oxidation, the chromium is going to be reduced into the oxidation state of +3, right? So let's see what is the number of electrons being exchanged within this chemical. So before the oxidation reduction reaction, so we know that potassium is providing +2 of the oxidation states, right? And then the oxygen is providing -14 because we know that all the oxygen is going to be in a state of -2, right? So the 2 chromium elements or atoms here are going to cover a oxidation state of +12. So each of them is going to be an oxidation state of +6, right? So after this oxidation reduction reaction, the chromium is going to be reduced to +3. So what that means is that there is a net exchange of electron or 3 electrons per chromium atom or chromium element. So there are two of them, which means that the Z here is going to be 2 times 6 minus 3, which is going to give us a number of electrons of 6. We also know that the molecular weight of the potassium bichromate is equal to 294. So this is going to give us an equivalent weight of 294 divided by 6, which is 49. Okay, so this is how we can calculate what is the equivalent weight for a single species for the oxidation reduction reaction. So you can see the difference from the calculation for the acid-base reactions. And we can also use the parameter of the milliequivalents per liter. So basically, milliequivalents per liter means 10 to the -3 of the molarity. So how do we apply these different units into the analysis of a solution? So here I give an example. So it wants us to calculate the concentration of sulfuric acid in milligram per liter. So also notice that for diluted species or diluted solutions, milligram per liter also is equal to ppm, right? Also in molarity and normality. For 93% sulfuric acid, so the remaining 7% is composed of water. So it has a specific gravity of 1.84. So what this means is that the density of this solution is 1840 gram per liter, right? So because we know that the specific gravity is in terms of the water, right? So water has a density of 1 kilogram per liter, which means that the density of the sulfuric acid solution is going to have this value here. Okay. So further, we know that this solution contains 93% of the sulfuric acid. So now we know that the if we want to show the mass concentration, then we have to calculate based on the density, right? Because 93% of them is going to be equal to is going to be represented by the sulfuric acid, right? And further, we can convert this unit into the values in milligram per liter. So this is how we can solve it, right? So we have 1840, and then we multiply that by 93%, and this is going to give us 1711.2 gram per liter, right? Further, we want to show these values in milligram per liter, so that's why we have to further multiply by 10 to the third to show the values in milligram per liter. Okay. So then, since we have the mass concentration, how do we calculate molarity? So we can directly use the mass concentration and divide that by the molecular weight of sulfuric acid to get molarity, right? So basically, we have to calculate what is the molecular weight. As we have shown before, the molecular weight of sulfuric acid is 98, right? In order to calculate molarity, we can directly divide the mass concentration by 98, and that is going to give us 17.5 m. This is showing in the molarity. And in terms of the normality, we know that this is basically for the sulfuric acid, it's providing 2 protons, right? So considering that it's providing 2 protons, then we just need to multiply that by 2. And then that is giving us a normality of 35. So now let's go back to the definition of the normality and see what that really means. So in terms of the normality, it is defined as the number of equivalents per liter, right? So it can be calculated based on the mass concentration divided by the equivalent weight. And as we have shown, the equivalent weight can have different values, right? Depending on how many protons being accepted or released for the acid-base reactions, or how many electrons being released or accepted in the oxidation reduction reactions. And because for the sulfuric acid, the equivalent weight is half of the molecular mass, which is 48, then that's why we can basically multiply the molarity just directly by 2 to get the normality here. So now let's do a quick quiz here. So if we have a solution that contains 0.1 m, so notice this is the molarity of the sodium carbonate. So what is its normality, right? So the normality is going to be equal to 0.2 n here. So basically we can do that in a complex way, because we know that the molecular weight of the sodium chloride is going to be 46 plus 12 plus 48, right? Which is 106 gram per mole. So we can first convert this molarity into mass concentration, and that can be quite easily done by just using 0.1 multiplied by 106, right? So this is giving us 10.6 gram per liter. Okay, so what is the equivalent weight of sodium carbonate? That is 53, right? Because it's going to be able to accept 2 protons. So the way we calculate normality, N is going to be equal to the mass concentration, 10.6, divided by 53, and which is basically equal to 0.2 N here. Okay? Or we can just think of that in a more simpler way, because since we already know that the molarity is zero point 0.1, and we know that there are two charges or two protons that can be accepted, then its normality is just going to be 2 times or twice of the molarity, which is 0.2 n. And now we can take a look at the buffer system. So what is a buffer? A buffer is a solution that can resist large pH changes when the acid or base is being added or when it's being diluted. And for example, a weak acid can be a buffer. Okay, so let's take the bicarbonate ion for example. So basically for bicarbonate ion, or for a solution that's containing bicarbonate ions, if we add hydrogen chloride into the solution, then the protons being released from the hydrogen chloride can bind with the bicarbonate ion, and we're going to form the carbonic acid. Okay, and if we're adding some base into the system, for example, sodium hydrochloride, right? So then these OH radicals or OH ions can react with the bicarbonate ions, and then we're basically going to form water and carbonate ions, right? So in this way, the pH can be buffered. So the pH is not going to directly get reflected from what is the concentration of the protons or the OH ions here. Okay. So that is why the carbon dioxide or the carbon dioxide, bicarbonate ion, or carbonate ion can form a buffer solution. And this is related with a series of reactions. So for example, the dissociation of the carbonic acid, right? So we know that the dissociation of the acid can give us 1 proton and 1 bicarbonate ion. And this reaction has an equilibrium constant of 10 to the negative 6.35. And in terms of further the dissociation of the bicarbonate ion, it can get dissociated into a proton again and a carbonate ion. And for this reaction, it has a equilibrium constant of 10 to the negative 10.33. So how does this affect the pH or affect the buffer system? Okay. So from this series of dissociation reactions, we're going to basically generate ions that's dependent on the pH conditions. And here is showing a basic diagram that's representing or showing the concentrations of these 3 different species under different pH values. So you can see that under very high acidic conditions or a low pH value conditions, then the solution is going to be mainly composed of the carbonic acid, right? So as the pH further increases, we're going to see the formation of the bicarbonate ion, right? And as we further raise the pH, for example, by adding OH ions into the solution, and then the bicarbonate ion are going to get reacted and finally form these carbonate ions, okay? And we have to mention that bicarbonate is very important. So this buffer solution is very important in our body, that is balancing the pH. Okay, so without this system, our body cannot function well. So with this information, how do we solve, or how do we look at the typical mixtures in in nature? Okay, so for an open system, as we have learned from our previous lecture, we know that the concentration of the carbonic acid is purely dependent on the carbon dioxide concentration in the atmosphere. And this is decided by the Henry's law, right? So we know that we can find out the Henry's constant for the carbon dioxide, right? So this is providing us a value of 10 to the negative 1.47 m per atmosphere, okay? And we also know what is the partial pressure of the carbon dioxide in the atmosphere. So basically, based on the Henry's law, we can calculate what is the concentration of the carbonic acid in water. Okay, so that's going to give us a concentration of 10 to the negative 5 m. And so again, m is equal to mole per liter, right? So how can we apply this into the calculation for the pH of rainwater? Okay, so if you consider for the rainwater, there's a complete contact between the liquid and the gas environment. And since our atmosphere contains carbon dioxide, which is the reason why we're having a certain amount of the carbonic acid in the solution, so this is going to give us a lower pH, right? So this lower pH, what this lower pH means is that the pH of this solution or pH of this rainwater is going to be lower than 7, because we know that 7 is neutral condition, right? Doesn't have any other ions, just purely hydrogen and hydroxide ions. Okay, so by having this condition, we know that if the pH is below 7, then there's no carbonate ions, right? So the solution is mainly just composed of the carbonic acid and the bicarbonate ion, right? So now we can use the relationship of the dissociation reaction for the first reaction here, because we can basically ignore this reaction since pH is lower than 7. So this is how we can solve it, right? So since we already have the concentration of the carbonic acid, right? And then further we know that the equilibrium constant for the first reaction, Ka1, is equal to 10 to the negative 6.35. And the equilibrium constant can be calculated by the concentration of the proton multiplied by the concentration of the bicarbonate ion divided by the concentration of the carbonic acid. So further, because of the, so as we have shown here, because the carbon dioxide is a weak acid, so right, the pH is going to be less than 7. Again, I'm going to draw it here. So we're not going to have any carbonate ions in the solution, right? So in this under this situation, the carbonate species can be ignored. So because of the charge neutrality, the proton concentration is going to be equal to the bicarbonate ions. So these two concentrations are the same. So then we can plug in the concentration of the bicarbonate ion. So we're going to have the square of the proton concentration divided by the carbonic acid concentration equal to 10 to the negative 6.35, right? So further, we have the concentration of the carbonic acid coming from here. So we can calculate what is the concentration for the protons. And based on the definition of pH, we're going to take the log 10, right, of 10 to the negative 5.7. And also, remember the negative sign here. So the pH is equal to 5.7. You can see that for the natural rainwater, it's going to be under an acidic condition, right? So also we can see from this graph here, so under a pH of around 5.7, you can see that the concentration of the bicarbonate ion is around a quarter of the carbonic acid concentration, right? So further, we have the definition of the buffering capacity. So the buffering capacity is defined as the ability to resist the pH change. So to represent this capacity, we need to define a new term or define a new parameter called the alkalinity. So alkalinity is defined or can be calculated based on the coming from the acid neutralizing capacity. So basically that is the acid used to lower the pH to 4.5, okay? So for the water system that only contains the carbonate species, then the alkalinity can be calculated by the concentration of bicarbonate ion plus twice of the carbonate ion, because the carbonate ion needs 2 protons to neutralize these species, right? And then we also need to consider the concentration of the hydroxyl ion, right? And also we need to minus the concentration of the proton ions. And also the alkalinity is shown in the unit of equivalent per liter. So basically, by convention, the alkalinity is expressed as the milligram per liter as calcium carbonate. So basically, we want to use the equivalent weight of calcium carbonate too. And we have already calculated that the equivalent weight of calcium carbonate is 50 grams, right? 50 gram per equivalent weight, right? So basically what we can do is we can first calculate the molarity of all of these acid neutralizing species, and then just multiply that by the equivalent weight. And then that is going to give us the alkalinity. So let's work on our final example here. So wants us to calculate what is the alkalinity of a solution that's containing 100 milligram per liter of the carbon ion, 75 milligram per liter of bicarbonate ion under a pH of 10, right? So according to the equation here for calculating the alkalinity, so we need to first calculate what is the molarity of all of these species that can neutralize the protons, right? So we need to notice that we have to multiply 2 in front of the carbonate ions, because one carbon ion can neutralize 2 protons, right? So then we can directly use the condition here, because we already know the mass concentration of the bicarbonate ion. We can directly divide that by the molecular weight of the bicarbonate ion, which is 60. And then we need to remember that we need to multiply 2 in front of this mass concentration. And for the bicarbonate ion, we can divide 75 by 61, which is the molecular weight of the bicarbonate ion. And also we need to consider the concentration of the hydroxide ion and also the protons, right? So under a pH of 10, then the hydroxide ion concentration is going to be 10 to the negative 4. And the concentration for the proton is going to be 10 to the negative 10. So also one thing we need to notice is that here, to calculate the concentration of the proton that can be neutralized, we were using the unit of milligram per liter, right? So we're calculating basically the milli equivalents per liter. So under this situation, we also need to multiply the concentration of the hydroxide ions by 1,000, because here we didn't convert that into gram per liters. So this is going to give us 4.6666 milli equivalent per liter, right? And finally, we need to multiply the equivalent weight of the calcium carbonate, which is 50 gram per equivalent, right? And multiply this number by 4.66, and that's going to give us 233 milligram per liter as calcium carbonate. Okay, so I hope that this example is clear enough, so we can use that to calculate what is alkalinity for certain species of solution, right? So now let's review the questions we have gone through in this class. So what is the difference between the density and specific weight, right? So for the density is just based on the mass of the species, right? And mass and the volume of the species, and specific weight is in terms of the water, okay? So also we want to understand how do we remove the colloid materials from the water. We can use filtration, right? We can also use centrifugation, right? What is the molarity and what is normality? So normality is dependent on the transfer of the electrons or the protons. And what is the difference between them? So how do we calculate the equivalent weight? How do we calculate the concentration in the milli equivalent per liter? So also what is buffer? What is bicarbonate? Why is bicarbonate at a buffer? That's because it combined with a proton, and also it combined with the hydroxide ions, right? Also, what is alkalinity, and how do we calculate alkalinity? And also, in an open system, which carbonate species is a constant? Okay,